Hello and welcome to yet another video of Cornerstones of Math. Today's problem is divided into two parts. We have a sequence an defined as the recurrence relation a1 equals 1/2 and an plus 1 is given as n squared divided by n plus 1 n plus 2 times an for all natural numbers n. Find the general term an and the sum of the infinite series, the infinite sum of an. When evaluating the series, you might want to use the famous known value of the Basel problem, which is that sum of 1 over n squared gives the value pi squared over 6. So first, finding the general term. It is easy because this is one of the simplest forms of recurrence relations, just an plus 1 equals an multiplied by something form. This means that we can keep substituting this an part on the right hand side using the given relation recursively. So if we apply this to an, then we have n minus 1 squared divided by n times n plus 1 times an minus 1, and then this an minus 1 is equal to n minus 2 squared divided by n minus 1 times n times an minus 2, and this an minus 2 is equal to n minus 3 squared divided by n minus 2 times n minus 1 times an minus 3, and we can go on and on until we have, at the very last part, we wanted to end with a 1 at the end, then the very last fraction must be 1 squared divided by 2 times 3. So this is the expression for an. Obviously, we have to cancel terms. If you have difficulties identifying the cancelling pattern, then just write down more terms on the front and in the end. So on the front, the next fraction will be n minus 4 squared divided by n minus 3 times n minus 2. Then we have n minus 5 squared divided by n minus 4 n minus 3, and n minus 6 squared divided by n minus 5 n minus 4, and so on. And in the end, first let's change this a1 with the given value 1/2. And here we must have 2 squared divided by 3 times 4, then 3 squared divided by 4 times 5, 4 squared divided by 5 times 6, and 5 squared divided by 6 times 7, 6 squared divided by 7 times 8, and so on. Here notice that n minus 1 squared at the numerator, and n minus 1 and n minus 1 at the denominator, n minus 2 squared at the numerator, then n minus 2 here and n minus 2 here at the denominator, then n minus 3 squared, n minus 3, n minus 3, and next n minus 4 squared, n minus 4, n minus 4, and we go on and on. So this n minus 5 squared will be cancelled, and this n minus 6 squared will be cancelled as well. This goes until these 3's are cancelled with these 3 squared at the denominator, and 4 here, 5, 5, 5, 6, 6, 6, and we can go on similarly. So these 2 7's will be cancelled, and this 8 will be cancelled as well. Moreover, after we substitute a1 with 1/2, this 2 squared at the numerator can be cancelled by these 2 at the denominator. So the numerator becomes 1, and in the denominator, we have n here and n here, and n plus 1 here. So we have n squared times n plus 1. So this is the general term an. Next, the sum of the series. First, we need a partial sum. The partial sum is the summation of 1 divided by k squared, k plus 1, from k1 to n. Here, let's use this given series as a hint. we are given the sum of 1 over n squared, so can we somehow isolate 1 over k squared when calculating the partial sum? Well, we know that if we have k plus 1 at the numerator, then 1 over k squared part appears. But the numerator of the general term is 1, so we must subtract this k. Notice that this gives the second term 1 divided by now k times k plus 1. And we can also carry out this summation by partial fraction. So we have the summation of 1 over k squared. And as for the next part, we use the partial fraction method, which gives 1 over k minus 1 over k plus 1. So we have the summation of 1 over k squared. And as for the next part, this is the summation where the terms get cancelled out. So we have this minus 1 over n plus 1. Therefore, the sum of the series an from n1 to infinity is the limit of the partial sum. Here, notice that the limit of this part becomes the infinite series that was given in the problem, which is pi squared over 6, and this part approaches 1, so the sum is pi squared over 6 minus 1. And that's all for today's video. Thank you for watching. Please don't forget to hit that like button if you enjoyed this video, and I will see you in another video.